Okay, I'll try to explain the Schrodinger equation. Okay. Okay. So from what we learned, Schrodinger equation is this one. Okay, it's this thing, and now I will prove it. So I'll start from my first. Before I prove it, I should explain what is Schrodinger equation first. So Schrodinger equation is an equation that explains how the quantum state of some system change with time. So they sound pretty hard, and so maybe you don't need to understand this thing, but okay. At first we must have a function, wave function first. Okay, so as name my wave function is psi, which psi depend on x and t, and of course they have two parts, the x, the distance, and the t, the time, the function of time. So on the eigenvector, the fx will be equal to e powered by I kx, and for on the time will be I minus e minus I omega t. Okay, and this will equal to e as I pull the I out, and kx minus omega t. Okay, so this is my equation. Now I will write on here. So my psi is psi. Okay, I'll just write psi here equal to e I and kx minus omega t. Okay. Now I want to differentiate this by x. Okay, this means I differentiate this the equation by x, and I will get this thing multiplied in. I will get I k and x gone. This is constant gone. We the same thing. I will replace it with the psi function, this thing. Okay, now I differentiate it again by x again. Oops. Okay, you will get the same thing again, right? So you will get I and k square. Oh, I write I square, right? And I is the imaginary unit, and 1i is equal to square root minus 1. And as you know, like square root 2, if you square it, you got 2. Same, I square equal to minus 1. Okay, so you get this thing is minus k square and psi function. Okay, I will say differentiate the wave function by time again. So I get this constant, so 0, and then I here, and I differentiate it. I will get a minus I omega, and t is gone, and I got the function again. So I wouldn't need this. I would need this and this. I copy that here. So I function differentiated by x 2 times equal to minus k square, and psi function differentiated by time equal to minus I omega and psi function. Okay, I remove this. Okay, now we have the wave component, the wave function here, and now I'll get to the Schrodinger equation. He came up with the energy. I'll say energy is energy, right? Okay, and before I explain energy, I want to explain the Hamiltonian first. Hamiltonian is the sum of the energy of the system. I say Hamiltonian of my fx. This is like if this is some wave function, Hamiltonian is like operator, like multiply plus something. So I say Hamiltonian of this equal to the energy of the function. Okay. Now I say that if you don't understand the Hamiltonian, it's okay. I'll explain it later on the end of the video. I says sum of the energy is the energy plus energy plus energy and all the component of the energy. But for the matter wave, from the matter wave which we are talking about, the sum of the energy, I'll just remove this sigma, okay, equal to E is the kinetic energy, and I don't like KE, I like EK, okay, and the potential energy. So E, okay, equal to EK, as you know, half mv square. And I say the potential energy, like in the one-dimensional box, in the 1D box, you say that this zone has a potential energy of 0, right? You say that this don't have a potential energy. So why? Because this thing and this EP is infinity and EP is infinity, like this, from this one particle in one-dimensional box, right? This one. So what I want to say is that this is just a value of the location of the particle. So I just say that it's a constant. Oh, not a constant. It's just defined it by the system. I state Vx. Okay. Now E equal to half mv square, right? I don't want a half mv square. I want some other form. I want some momentum. Ek is half mv square, and momentum is mv, right? So I square the both sides. P square equal to m square v square, right? So this are mostly like this, 2m, right? I move 1m down here. This gone, and hey, look familiar, but I need some half, so I multiply on both sides, and now you got the Ek. Now Ek is p square over 2m. Okay. Now p square over 2m plus some potential energy of the function. And now the energy of a matter wave, which I'll just say that it equal to h bar and omega. You can find the proof on like Wikipedia and everything. Now p square over 2m plus vx. Okay. I'll say I'll multiply on both sides by my wave function. Okay. And wave function equal to p square over 2m and my wave function plus the vx and my wave function, right? Okay, now we got this. Okay, I'll remove this thing, and now let's see from here. For the easier, I just copy this to here. Okay, now h bar. This side there is h bar, there's omega. Which one have identical? This one seems good. Okay, I copied this. Blue. I use green. The wave function differentiated by time equal to minus I omega and my wave function. So I move my minus I down here, so the wave function differentiated by time and minus in front, and the I this imaginary unit, and omega and psi. Something missing, the h bar, right? I multiply h bar on both sides, you got a h bar, psi differentiated by time over I, and minus in front equal to h bar omega, and my wave function on this side is the same now. Okay, I'll say I multiply only this side by I over I. Okay, they decrease, so we got just 1. Okay, I'll multiply I by I, and as you know, I and multiply by I is minus 1, right? Square root minus 1 multiplied by square root minus 1 equal to minus 1. Okay, now I will get the h bar, I come to the top, and psi t, and this thing you get minus 1, right? Decrease the minus in front, so I got only this equal to h bar omega psi. Now I replace I replace this thing here with this blue. So I h bar, I write this, differentiate the wave function by time, okay, equal to what? Okay, now this part I just move here. Okay, I'll use orange, p squared over 2m and psi. Let's see from the top which seem good. This thing seems good because we already used this one. Okay, so we got y differentiated by x 2 times equal to minus k squared and psi function. Now psi function here, I move this one down, so wave function x differentiated by x 2 times multiplied by minus k squared equal to wave function. I'll say I'll multiply both sides by p squared over 2m, p squared over 2m psi, and p squared over 2m wave function differentiated by x 2 times and k squared and minus in front, right, equal to this. Okay, now I got this, they are identical. Okay, but this I will do something more with it. I say that momentum momentum is mv, right? Now mv, as you know that I don't say this. As you know that the De Broglie equation, the matter wave equation, lambda is equal to h by momentum, right? I move this up and move this thing down. P equal to h over lambda, right? Then P, I say that P is h. I don't want a h. I want a h bar instead. H bar is h over 2 pi, right? I move this thing up and you got a h, right? So it's a 2 pi and h bar over a lambda. Lambda is what? Lambda is a counterpart of lambda we call k, right? Which is equal to the 2 pi over lambda. K is called an angular wave number. Angular wave number. Okay, we call it a k. 2 pi over lambda. I put it here. 2 pi over a lambda. Oh no, why do I do that? I move lambda up and move k down. I got a 2 pi over k, right? And I pull the k up because it divides. So p equal to 2 pi h bar k over 2 pi. 2 pi decrease. Momentum is h bar multiplied by the angular wave number. Okay. Now I replace momentum here to here. Okay. Now h bar k, right? So this is square, so you got h bar square k square over 2m and minus in front, and differentiate the wave function by x 2 times and k squared. Now you see what? K squared and k squared decrease. Okay? Now we got the h bar squared over 2m minus in front, and differentiate by x, my wave function differentiated by x 2 times. So like this and this. Okay. Now I write my this thing and this thing are equal. I put it here instead of this. Okay, I write now here equal to minus h square over 2m, and differentiate the wave function by x 2 times. Okay, now plus the same thing is the Vx of a psi. The Vx of psi is the what we call the potential energy of the function. Now we got what do we got here? This is a Schrodinger equation. But wait, Schrodinger equation isn't this? Well, is E, and on this, so that's E equal to that. And why do I say E equal to this at first? Well, this is a time dependent Schrodinger equation. So if I want a non-time dependent Schrodinger equation, I just replace the one that I differentiate here with the normal one, pink, which I say that my wave function differentiated by time equal to minus I omega, and my wave function, right, I replace here I h bar multiplied by minus I omega, and my wave function, correct, equal to minus h square over 2m, and copy that down. Okay, I again minus 1 minus decrease, so h bar omega, my wave function equal to minus h square over 2m, my wave function differentiate my wave function 2 times by x, right, plus potential energy of my function. Okay, now I'll change this back to E. So this is E, right, as I say from here, E. So this is E of my wave function equal to this thing, and this thing we call a Hamiltonian operator. So it's equal to Hamiltonian operator, and this is the shortest form of a time independent Schrodinger equation. And I expand this thing out, I will get h bar omega, my wave function, equal to minus h bar square over 2m, my wave function differentiate my wave function 2 times by x, y, z, all the component, and then plus a Vx, the potential energy of my wave function. So this is the one more thing, this thing we may call this a gradient operator, which I think we'll learn in calculus, I think. So no, physics. So this is the complete form of a time independent Schrodinger equation. That's it. We just proved the Schrodinger equation.